Our next talk is by Professor Anant Godbole. And I should mention that we were colleagues many years ago in 1986, I believe. 85, 86, I think. It was in Michigan Technological University. And of course, Anant was also from ISI, as many of us know. And I invite Anant to present his talk on birthday and coupon collector problems with dependents. Anant. You have to unmute probably.
Yes. Good morning, everyone. Thank you for coming to my talk. I will be sharing my screen shortly, but I just wanted to thank the organizers, particularly Professor Karantha and Bapat, and also Nupur Nandini for all her help. And I will share my screen now, and we will get started. Okay, the topic of my talk today is the birthday and coupon collector problems, but not the regular ones. The ones I will review the theory of those, but I'll be looking at the situation where you've got a lot of dependence. And the topic that I've chosen to talk about is covering and packing designs. So let me reminisce a little bit about something that came to my mind quite vividly. About 43 years ago, I was an MSTAT student at ISI Delhi. And Professor C.R. Rao had a seminar, or maybe it was a joint seminar, but he would assign papers in which that we had to present, read and understand and present. And one of the papers was on the Kramer-Rao inequality. And it was written by, it was a preprint actually, and I think it has changed since that time. Anyhow, it was written by my professors Fabian and Anant, my later to be professors, when I would go soon after that to Michigan State University for my PhD. And I got together with a PhD student, Varadaraj Perumal, who was a student of Professor KRP. And we concluded together that the contributions in the paper were not quite as significant as claimed. And it was really a happy moment for me, but I got, got the paper a few weeks ago and tried to reconstruct what it is that we had done. And I'm sorry to report that I could not reconstruct what had been done. But let me toggle to the paper itself. It appeared soon afterwards in the Annals of Statistics, Volume 5, 1977. And the claim here is that there are sufficient conditions which are weaker than the traditional ones. And what Peru and I came up with was an argument that they were in fact equivalent. But as I said, I've been away from statistics for at least 30 years, and it was not an easy thing for me to do. Okay, so what will I be talking about today? First of all, I'll introduce the classical birthday and coupon collector problems, which I will rephrase in the format of packing and covering. And then we'll see to what extent the results and not just the results, but the nature of the results and the log factors, all that show up again when you look at covering designs. So, birthday problem. Suppose we're trying to pack balls in boxes at random so that each box contains at most one ball. Okay, and the point is that this is the so-called birthday problem because the moment you get a box with two balls, so the boxes are the 365 days of the year. The balls are the people's birthdays. They go into the appropriate box. And we're trying to, let's recollect that when capital N is 365 and small n is 23, then that is the time at which the probability of having a birthday coincidence goes over 0.5 for the first time. However, in this talk, I'll be interested more in thresholds, probabilities that go to 0 or 1. And one of the things in Barber and Holst, 1989, and it's been known before that, actually, it's in Feller Volume 1. A lot of this is in Feller Volume 1. If we throw little n balls into capital N boxes, the property holds with high or low probability at the threshold n equal to the square root of n. In other words, if little n is significantly smaller than the square root of n, smaller by an order of magnitude, this implies that there's the chance that there is a box with 2 or more balls tends to 0. On the other hand, when little n goes substantially larger than the square root of n, then the asymptotic probability of a coincidence is 1. And if you look at the square root of 365, it is about 23. So you're looking at the threshold when that happens. There's a generalization of this to at most g number of balls. It's again classical, but we re-derived it in this paper. This paper, by the way, is joint with 3 students, Thomas Grubb, Q.T. Han, and Bill K. And we used Talleyrand's inequality to do it. So here's the result. So when little n balls are randomly and uniformly distributed in capital N boxes, then if you define a random variable x being the number of boxes with g plus 1 or more balls, so when g is equal to 1, you get 2 or more balls, then if n is substantially smaller than or larger than capital N to the g over g plus 1, that tells you the probability that x is equal to 0 goes either to 1 or to 0. I've written this a little bit differently from the birthday problem. So when n is small, the chances that there are no boxes with a large number of balls goes to 1, which is what, it's an inverse way of saying what I did on the previous slide. So yeah, and when g is equal to 1, you get the square root of n. If you're looking for the threshold for 3 or more balls in a box, then that's n to the 2/3 and so on. But notice that the thresholds up here get closer to n equal to capital N as g goes to infinity, because the exponent approaches 1. However, it might still be the case that if you have n larger than capital N, it might be that not all the boxes will have a ball in it. So this is now leading to the coupon collector problem. So in terms of birthdays, how many people do you think you need to have before at random if each box is to have at least 1 ball in it? So that's the coupon collector problem, and it's again classical. You will find in Feller Volume 1 that the expected waiting time for each of the boxes to be filled is kind of interesting. It's n times log n, that's the leading term. Then n times Euler's constant is the second order term. And then you have n times something going to 0. So that's the error, I guess. And so that's roughly n times log of n is the waiting time. And the variance is roughly n squared. And there's constants, I think it's 6 over pi squared. So we've looked at each box containing at most 1 ball, at most g number of balls. Then you've looked at least 1 ball. This is coupon collection. So the question is, what about at least g number of balls? This is the result I'd like to focus on because it's the most nuanced of the lot. So this is a theorem that was proved by Lars Holst, and it generalizes previous work, but it's very definitive in its content. So it says that if you look at the waiting time until each box has at least g number of balls in it, then the expected value is your n times log of n, right? There's the Euler's constant. There's little o of 1. But this term over here, g minus 1 log n, is the most intriguing of the lot. It tells you that successive coverings of all the boxes are linear, but not in log n, but in log n. So this is the part that tells you that subsequent covers take lesser time and in the same kind of way. Then if you normalize this by dividing V of G by N, and then bringing those other terms over to the left-hand side, what you get is the distribution is extreme valued here of the, yeah. And if you, this talk is focused on thresholds, so you can easily take the previous result and make it into a threshold result. If X is the waiting time till each box has at least lambda number of balls, then the probability that X is less than or equal to so much goes to 1. But what is that so much? It's n log n plus lambda minus 1 log n plus anything that goes to infinity. Okay, so the chance that you get what you need in so much goes to 1. And it's the a sub n that dictates the fact that it goes to 1. Likewise, the chance that X is less than n log n plus n times lambda minus 1 times log n minus bn, that's a smaller number. The chance that you have X being less than or equal to that approaches 0 as n goes to infinity. Okay. All right, so let me switch to combinatorial designs. And over here, what we're trying to do is slightly different. So let's talk of a set of size n, that's your base set. And your job is to look at every set of size t, right? That's, you can think of those as your boxes. And what you're doing is selecting as few sets of size k so that every t set is contained in at least one k set that is picked. Of course, k has to be greater than or equal to n. There's an easy lower bound, n choose t divided by k choose t, which you can get by a simple counting argument. And what this combinatorially simplifies to is actually n choose k over n minus t choose k minus t. And this formulation is in some sense better because it gives you the fraction of all the k sets that you need to pick in order to cover every set of size t. And cover is in the set of set inclusion. So you need at least that many. And what the Erdős-Hanani conjecture is that this number is actually asymptotically correct if k and t are held fixed and you allow n to go to infinity. So yeah, and this was proved first by Rodel. But what if n is not going to infinity? If you just have n, k, and t, then you have this kind of an upper bound that Erdős and Spencer proved. N choose t over k choose t times 1 plus log of k choose t. Notice that this is also can be written as n choose k over n minus t choose k minus t. Then a couple of students and I got together about 25 years ago and found a result that said that actually if you want the smallest number of k sets so that each t set is contained in at least g of them, then interesting things happen. You get your n choose t over k choose t. Here's your log k choose t. But what you actually get is subsequent coverings need just log of k choose t. Same thing, the same kind of phenomenon. And so that is very interesting. But these results here and on the previous slide are looking at the minimum number of sets that you need. It's not looking at random behavior. So let's get into that. Let's start with the birthday problem. Now, so what you have is C is a collection of sets of size k, in which each set of size k, each element of n choose k, is selected for membership with probability p. And what you're interested in is the number, you're interested in every t set being contained in at most lambda numbers of k sets. So we're looking at the at most problem, just like the birthday problem. So x equal to x lambda is the number of elements which are subsets of at least lambda plus 1 members of C. And then if p is small, that tells you that you have a small number of k sets then the chance that there's no such set goes to 1. And if P crosses that threshold, the probability approaches 0. Thing to keep in mind is that if lambda goes to infinity, this part of the exponent approaches 0, and you're looking at a threshold at 1 over n to the k minus t, which is, if t and k are constant, then what you're looking at is something which is roughly the same fraction of sets that you had in the lower bound. Okay, so that was the packing result. And then for the covering result, what Svante Janssen and I got together and proved is that the cardinality threshold for single coverage is so much. So if you have n choose t over k choose t, which is n choose k over, here we go, it's n choose k over n minus t, k minus t, times log of n choose t. So the threshold number is a little bit larger than k choose t, plus or minus omega 1. Omega 1 is any function going to infinity. So if you have a large number, this much plus omega 1, then the chance that you've covered all the sets is it's a covering design with high probability, right? In other words, all the t sets are covered by a k set. And when you have minus omega 1, then the probability of that happening is low. It goes to 0 asymptotically. You might ask, what happens if you have log of n choose t plus some constant? And that too is in that paper. It shows that there's the number of uncovered t sets has a Poisson distribution with an appropriate mean. Now, in this work that I wanted to talk about, this is work that has been submitted to the Journal of Combinatorics. It's still under review. And in that, there's this covering and packing designs. There's also a section on CDON sets from additive number theory, union-free families, which is random subset theory. Anyhow, the point here is that let's take a look at this. What you get is that the threshold is, as announced before, for 1 coverage. You're interested in each t set being covered by at least k sets. So you have the previous number, you have the omega 1s, but then subsequent coverings take g minus 1 times choose t. And this is the part that I wanted to draw your attention to. I'm looking at the clock. I'll try and summarize the proof rather than try and go over it in any detail. You have a sum of indicator variables, x, and you want to approximate the distribution of x with the Poisson distribution. And the Stein-Chen method of Poisson approximation relies on the existence of a coupling sequence which models the distribution of the indicators conditional on the jth one being equal to 1. And if such a coupling exists, which is monotone in the sense that those j's are larger than i's, then the total variation distance can be expressed in just in terms of the mean and variance. Well, for the Poisson distribution, the mean is equal to the variance. So if a distribution is close to Poisson, you'd expect that this difference would be small. And then you'd have the distance going to 0. That's the rough idea. On this page, I'm describing the coupling. If I sub j is equal to 1, in other words, if the jth set is covered lambda minus 1 times or less, then you don't need to define j's any differently. On the other hand, if you have overcoverage, you're going to remove a certain number of k sets according to the appropriate distribution so that you get a sample outcome corresponding to I sub j equal to 1. And the deselection tells you that you must have j greater than I. Simplify the Stein-Chen bound, you get something like this. It really amounts to covariance calculation, the probability that both the first set and the jth set are covered lambda minus 1 times. And then you have 2.5 pages of pretty intense analysis, gives you the result. Okay, and here are the references. And once again, thank you very much for coming to my talk. I'm going to stop sharing and say hello to you and
thank you, Anant.
See if questions. Thank you.
That's an interesting talk. Has lots of information, lots of interconnections, and any questions? We have time for a couple of questions. Are you in Atlanta, Anant?
No, I'm in Johnson City.
Oh, Johnson.
It's close to Atlanta.
Yeah, I know. Yeah. Okay. All right. Okay. Yeah. Very nice. Nice to see you too.
Nice to see you, KPS.
Appreciate your talk. Very interesting. Okay. Thank you.